Hey guys, welcome back to our channel. If you're new here, my name's Dakota.
And I'm Hallie.
And today we're going to talk about the differences between dynamic range and sensitivity,
as well as the differences between range precision, resolution, and accuracy. Dynamic range is an indicator of sensitivity. It refers to the range of usable signals a device can detect. Sensitivity in a receiver is taken as the minimum input signal required to produce a specified output signal, having a specified signal-to-noise ratio, and is defined as the minimum signal-to-noise ratio times the mean noise power.
In simpler words, sensitivity is the smallest a signal can get in comparison to the noise figure before the signal is disrupted by the noise. For example, let's talk about amplitude-modulated AM and frequency-modulated FM receivers. An FM radio receiver can detect a frequency range of 88 to 108 MHz, whereas an AM radio receiver can detect carrier frequencies from 535 to 1,605 kHz.
FM radios have a decrementation of 200 kHz, whereas AM radios have a decrementation of 10 kHz. The dynamic range of the radio receivers is based on factors such as detectable target size and detectable target range.
Both AM and FM radios pick up on a specific range of signals to avoid signal overlapping and miscommunication. In order to function separately, AM radios detect signal frequencies much smaller than the signal frequencies that FM radios pick up.
If the frequencies fell into the same size range, the receiver would risk mixing up the signals and errors in processing would commonly occur. Range precision is a measure of the ability to sense small changes in the target's position. For example, an interferometry radar has a high level of range precision and can be used to detect subtle movements in the target. These radars can be used to detect someone's breathing patterns.
As the chest rises and falls, changes in position are not extreme, although can be detected due to the precision of the radar's range. If the target of the radar is set to a distance of 0.1 meters away from the receiver can detect the movement of the chest to the nearest millimeter.
On the other hand, a Doppler radar can be used to detect the speed of an object in motion relative to another object, typically the radar. These radars also have a high level of range precision because the radar is receiving a signal from the moving object to detect changes in speed.
For example, a Doppler radar can detect the speed of a car from meters to seconds to kilometers per hour. This means that there is a large range that a Doppler radar can detect in terms of speed, thus allowing higher precision when it comes to detecting changes in speed.
With both the interferometry and Doppler radars, the precision depends on the range. The range of an interferometry radar detecting someone's breathing patterns will be just as precise as the Doppler radar detecting the speed of a moving object, even though the ranges vary greatly in terms of distance and measurement.
The small incrementation of the detectable range can give us an idea of how range precision works, because the smaller the incrementation to overall range, the higher precision level will be.
Range resolution is the minimum distance two objects can be separated from each other and still be resolved as two separate targets. Here we have two scenarios depicting two airplanes flying close to each other. In the scenario on the left side of the screen, the radar transmits a signal towards the two targets and sends back two separate signals to the receiver.
Because the two airplanes are detected separately, two peaks are shown on the graph, meaning that there are two different targets being detected. Because the two targets are detected separately, there is a good range resolution for the radar because the two targets were far enough away from each other for the radar to pick up on.
On the other hand, in the scenario on the right side of the screen, the radar is transmitting a signal towards the two targets, and only one signal is being received even though there are two targets. The distance between the two airplanes is too small for the radar to pick up on, so only one peak is represented on the graph.
Because there is only one peak, only one target is being shown to the receiver, even though there are two airplanes. Therefore, there is a poor range resolution, because the radar cannot differentiate the two targets.
Range accuracy is the absolute error with respect to Earth reference, and it is related to the total tracking error. It includes the errors that continually affect the tracking accuracy to a certain level, systematic or bias errors, as well as the errors which affect tracking accuracy more or less on a random basis, noise errors.
Noise interferes with the precision of the radar because the radar is detecting the noise on top of what the radar is intended to detect. For example, there is an ideal pulse transmitting a signal back to the radar, but the actual measurement is the noise plus the pulse, which is different from the true results the radar is intended to pick up.